Okay, so last time we talked about the basic properties of radiation, and today we're going to talk about a specific kind of radiation referred to as blackbody radiation. Now, at the end of the last screencast, we talked about how all objects are continuously emitting and absorbing radiation. And we mentioned how most objects will emit some wavelengths and absorb some wavelengths better than others. Now today we're going to talk about a certain kind of object, a special kind of object, referred to as a blackbody. And a blackbody is a special kind of object in the sense that it actually absorbs all the radiation that's incident on it, regardless of the wavelength. So a blackbody is defined as a substance that absorbs all incident radiation, regardless of wavelength, completely. Now, where this name, blackbody, comes from is that if you shine light, or just more generally radiation, on a blackbody, there's not going to be any reflection because all of that light will be absorbed. So you're not going to see any reflected light. But in some sense, the name is actually a little bit misleading because although a blackbody won't reflect any light, it does emit light. Blackbodies do emit light, and so it won't actually appear black. It's going to appear whatever color it's emitting. Okay, so having said that, so if a blackbody is defined to be an object that absorbs all incident radiation, then what's its absorption spectrum going to look like? If you remember back, an absorption spectrum is a figure or a diagram that shows the fraction of radiation that gets absorbed at any given wavelength here on the bottom axis. So if you have some particular wavelength, this tells you the fraction of energy that gets absorbed at that wavelength. Now, by definition, a blackbody was something that absorbs all incident radiation. So what's its absorption spectrum going to be? Well, it must just then be a straight line across at 100% because it absorbs 100% of the incident radiation regardless of the wavelength. Now, why do we care? Well, it turns out that both the sun and the earth, to a first approximation, emit and absorb energy as blackbodies. It's not perfect. The sun is actually closer to a blackbody than the earth. The earth ends up actually reflecting about 30% of the incoming radiation, but at least to a first approximation, it behaves pretty close to the way a blackbody would behave. Now, as I mentioned, a blackbody does emit radiation. And in contrast to absorption, it actually doesn't emit all wavelengths of radiation equally. It emits some wavelengths better than others. And if we look at the emission spectrum of a blackbody, it always has a specific kind of shape to it. It always has the same shape. So if you remember what an emission spectrum is, it's showing the amount of energy emitted of an object here on the vertical axis at any given wavelength. So if you choose radiation of this wavelength, it tells you how much energy is emitted at that wavelength. And when you look at the emission spectrum of a blackbody, it turns out that it always has this sort of bell shape to it, kind of like shown here in the figure. It's a little bit of an asymmetric bell shape, so one side's a little steeper than the other, but it always has this kind of bell shape to it. It's called a blackbody curve, blackbody emission spectrum. Now, some of the properties that we might be interested in this emission spectrum are the following. So the first property we might be interested in is the total amount of energy that the object is emitting. So I'm going to call that E. So E is going to be the total amount of energy emitted by the object. Now, in terms of the spectrum, the total amount of energy emitted actually turns out to be related to the area under the blackbody curve here. If you've got more area under the curve, that tells you actually that you have more energy being emitted. But because the blackbody curve always has the same shape to it, we can just tie the amount of energy emitted to the height of the peak, because the peak goes up and down, but the shape always stays the same. So as soon as we know what the peak is, we actually know what the shape of the curve, or what the actual curve is going to look like. It's just going to have that particular shape passing through that peak. So for the purposes then of our discussion, we can tie the total energy emitted to the height of the peak here, the height of the peak of our emission curve. The second property we might be interested in then, so the total energy emitted we tie to the height of the peak of our emission curve. The other property we might be interested in is where does that peak occur? That is, what wavelength is emitted most strongly by your black body? What wavelength has the peak of your emission curve? So the idea here is that the emission spectrum is telling you the amount of energy emitted at any given wavelength. So wherever the peak is found, that's telling you that that's the wavelength that's being emitted most strongly by that object. And it turns out that both of these two properties, the amount of energy, which is sort of the height of the peak, and the actual wavelength at which the peak is found, both of those guys end up being tied to one property of the object. They actually are determined completely by just the object's temperature. They're both determined by the temperature of the object. And the basic rule is that an object that's warmer will emit more total energy, so greater E, more total energy, and the wavelength that it emits most strongly will actually be shorter. So the peak of your curve will then be found at a shorter wavelength. The wavelength that gets emitted most strongly is actually a shorter wavelength. So the warmer it is, it emits more energy, and it emits shorter wavelengths most strongly. Now, the warmer part, the total energy part, should be relatively intuitive. As the object gets warmer, it has more energy. You might expect it to emit more energy as well. The peak of the emission curve, that's a little bit less intuitive. But for all of you who happen to have had summer internships in blacksmith shops, if you've ever worked in a blacksmith shop, you'll sort of be familiar with this, because when you're heating up metals in a fire in your blacksmith kiln, you're going to see that those metals actually change colors as they warm up. So they'll start off just being whatever color they are, and then once they warm up enough, they're going to go through a series of colors, starting with red, and then becoming more orange, and then sort of more greenish bluish, and then sort of more bluish. And what's going on there is, as that metal is warming up and it's emitting, kind of like a black body, the wavelengths that it emits most strongly go to shorter wavelengths as it gets warmer. And if you're in the visible part of the spectrum, then your eye is interpreting those shorter wavelengths as different colors. So as it warms up, it emits different colors most strongly. So what's this look like then in terms of our diagram up here? Well, if we have an object that's warmer, it's going to emit more energy, so its peak is going to be higher along the energy emitted axis. And it's going to emit shorter wavelengths more strongly, so the location of the peak is going to shift towards shorter wavelengths. So it might end up looking something like this. So that's going to be a blackbody curve for a warmer object. And if it's warmer still, then it's going to be higher peak and at shorter wavelengths. So maybe something like this. So that's going to be a warmer object. By contrast, if you have a colder object, then it's going to emit less energy, so the peak gets smaller, and it's going to emit it most strongly at longer wavelengths. So a colder object might look something like that. So the peak drops, emits less energy in total, and it emits most strongly at a longer wavelength because it's colder. It can be useful to go through and connect all of these peaks of the different objects here with the different temperatures, and you end up getting a curve that looks something like this. So that's the curve that shows your peak emission. So you're getting, for your objects that are colder, the wavelengths that are emitted most strongly are up here, and then as they get warmer, they sort of fall back on this curve so that you're emitting shorter wavelengths more strongly. This is the emission spectrum of the sun. Again, the sun behaves pretty closely to a black body. You can see it has the same asymmetric bell shape to it. We've actually seen this before when we looked. This was our example of an emission spectrum. So again, what we've got is the amount of energy being emitted here on the vertical axis and wavelength on the bottom axis. So at any given wavelength, how much energy is emitted. And you can see that the peak of the sun's emission spectrum is found down here in the 0.4 to 0.7 micrometer range. And if you remember back to the previous screencast, 0.4 to 0.7 micrometers, this sort of narrow band right in here, is actually the visible part of the spectrum. So that's why they're showing it with these colors in here. So maybe it shouldn't be a coincidence then that the part of the spectrum that our eyes are most sensitive to is, as it turns out, the part that's emitted most strongly by the sun, because that's the radiation that, is most prevalent in our environment. And so that's the part that our eyes are most sensitive to. If you go through and add up the total, it turns out that about 44% of the radiation emitted by the sun is in this little band here, the visible part of the band, or the visible part of the spectrum. And then as you go towards longer wavelengths, towards the infrared, the amount of energy decreases. The amount of energy being emitted infrared decreases. And as you go to shorter wavelengths, you go towards ultraviolet, and you're emitting less energy in the ultraviolet as well. Now, we can actually quantify these things because it turns out that the relationships between the energy emitted and the wavelengths emitted most strongly and the temperature are pretty straightforward relationships. And the relationship that tells us the amount of energy emitted and its relationship to temperature is referred to as the Stefan-Boltzmann law. The Stefan-Boltzmann law. And it looks something like this. The total energy emitted by the object, E, is just going to be given by some constant here, represented by this symbol. That symbol is actually the Greek letter sigma, adding to our list of Greek letters here, times the temperature to the fourth. Now, the sigma thing, I'm not going to give you the numbers for that because I'm not going to make you do calculations for it. But the main point is that it's a constant, so it's the same for all objects and for all temperatures. It's just some constant value. So what this is saying is that the total energy emitted goes like temperature to the fourth power. So as the temperature goes up, as the object gets warmer, it emits more energy. And it actually increases relatively quickly because the fourth power increases relatively quickly. If you double the temperature, then that's going to give you 16 times as much energy being emitted. Now, there's two details here. The first is that in order for this to work, the temperatures have to be expressed in Kelvin. And the second detail here is actually up above, which is that this is actually telling us the amount of energy emitted per unit area. So if you go and take any little bit of area on your black body, this is telling you how much energy that this little bit of area is emitting. And then to get the total energy emitted, you actually have to add that up over the whole area of the object. So bigger objects will naturally emit more energy because they have more surface area to emit. And this is the amount per unit area. So now let's put our Stefan-Boltzmann law to work here and think about the energy emitted by the sun and by the Earth. For the Earth, we can estimate the temperature of the Earth, sort of the mean temperature of the Earth, to be somewhere around 300 Kelvin. That's a little bit high. The actual mean temperature of the Earth is more like 288 or 289, but for the purposes of estimation, we'll just round that up to 300. And for the sun, the mean temperature of the sun, the part of the sun that emits the most energy, is like 6,000 Kelvin, roughly. The temperature is more like 6,000 Kelvin. So if we go through and take the ratio then of the amount of energy emitted by the sun to the amount of energy emitted by the Earth, it's going to look like this. So the energy emitted by the sun, E sub s, over the energy emitted by the Earth, is going to look like sigma times the temperature of the sun to the fourth, Stefan-Boltzmann law, over sigma temperature of the Earth to the fourth, and the sigmas here are just constants, so they're going to cancel top and bottom, so you're going to end up getting the ratio of the temperatures to the fourth power. So that's going to look like roughly 6,000 for the sun to the fourth power, over roughly 300 for the Earth to the fourth power. And 6,000 divided by 300 is 20. So this is going to look like 20 to the fourth. And 20 to the fourth, finally, is 160,000. So what this is telling us is that the sun, being much warmer, is emitting 160,000 times as much energy as the Earth. And you should keep in mind, again, that this is actually energy per unit area. So what this is really saying is any given little bit of area on the sun is emitting 160,000 times as much energy as the same amount of area on the Earth's surface. The sun being a whole lot larger, that means that the total amount of energy emitted by the sun is, that much larger compared to the Earth's amount of energy emitted. So moral of the story is the sun emits a lot of energy. Okay, what about the wavelengths emitted most strongly, the peak wavelengths? Well, the relationship telling us about the peak wavelengths is referred to as Wien's law. Wien's law. And what Wien's law tells us is that the wavelength emitted most strongly, lambda max, looks like, again, some constant, in this case we'll call it B, divided by the temperature. So as the temperature gets warmer, as the object gets warmer, the temperature being in the denominator, then the wavelength being emitted most strongly gets shorter. So the warmer objects emit shorter wavelengths, just as we were saying before. Now again, T here has to be in Kelvin, just like it was in the Stefan-Boltzmann law. And B is a constant. And this time I'm going to give you guys the constant roughly, just because I want to use it for calculations down below. You don't have to remember this. If I ever made you guys do calculations, I would just give you the constant. But the constant turns out to be about 3,000 micrometers times Kelvin. 3,000 micrometers times Kelvin. So let's put this to work to try to estimate the wavelengths emitted most strongly by the Earth and the sun. So for the Earth, Our lambda max looks like our constant B, which is about 3,000 micrometers Kelvin, divided by the temperature of the Earth, which was about 300 Kelvin from the previous slide. So, of course, the kelvins, the units Kelvin cancel, just leaving with micrometers, which is what we expect for wavelength. It's a distance, micrometer. And then 3,000 divided by 300 is about 10. So the Earth is emitting most strongly at wavelengths of about 10 micrometers. What about the sun? Forgot to fill that in. So if you go back to the previous screencast and look and see where 10 micrometers falls on our spectrum, 10 micrometers is solidly in the middle of the infrared range. So the Earth is emitting most strongly at infrared wavelengths of radiation. What about the sun? So for the sun, again, the constant's the same, 3,000 micrometers Kelvin. But the temperature of the sun, for the part that emits, is much higher, and it's more like 6,000 Kelvin. 6,000 Kelvin. So you take that one and multiply it out, or divide it out, and it's going to tell you that the sun emits most strongly at about half a micrometer, which is consistent with the previous figure. And thinking back to the previous screencast, half a micrometer is going to be right in this little band that we're calling visible. Visible runs from about 0.4 to 0.7, and the sun's maximum emission is going to be right in that band, about half a micrometer. So the sun, being much warmer, then emits most strongly at a shorter wavelength, about 20 times shorter wavelength. And so because of that, as a shorthand, we often refer to the sun's radiation as shortwave radiation. Shortwave radiation. Because, again, the maximum emission of the sun is at a shorter wavelength than for the Earth. And by contrast, we refer to the radiation emitted by the Earth as long-wave radiation. Because it's in the infrared, it emits longer wavelengths. So this figure down here is sort of trying to illustrate that. You've got your radiation spectrum of the sun here, with the peak emission occurring here in the visible part of the spectrum, down here at about a half a micrometer. And then over here, they actually had to break the axis over here because the Earth's peak emission is way over here at about 10 micrometers, so it's about 20 times longer wavelengths. And so it's got its peak way out over here. So they're kind of separated in this way. Peak emission occurs at very different wavelengths. Now again, this isn't anywhere near to scale because if you look on the vertical axis showing the amount of energy emitted for the sun, it's in units of 10 to the 7th. And then over here for the Earth is 24. So again, this isn't anywhere close to scale, but it's just trying to illustrate that the sun emits much more energy and emits it at a shorter wavelength, and the Earth emits less energy at a longer wavelength. Short wave, long wave. Okay, so with that, we'll take a break here, and when we come back, we'll start contrasting blackbody radiation with objects that absorb some wavelengths better than other wavelengths.